Have you ever wondered why glass is transparent? I mean, whether it's glass or this piece of metal, their atoms are made up of the same neutrons, protons, and electrons. The neutrons and protons in glass are just like those in metal. So why can you see through glass but not through a metal block? But a metal block is opaque. A foreign blogger showed a piece of graphene. If you look closely, there's a faint black spot in the middle of the glass sheet. This is graphene, just one carbon atom thick. The gaps between atoms let 97.7% of light pass through, making it appear transparent. So, it looks transparent. However, with multiple layers of atoms, the gaps fill up, blocking photons. Thus, the material becomes opaque, like a sheet of graphite paper. But why is glass transparent regardless of its thickness? On the internet, the most common explanation you can find is this: atoms are hollow. If you think of an atom as a stadium, the nucleus is the size of a pea, and the electrons are like grains of sand in the stands, leaving large gaps in the atom for photons to pass through. So, instead of asking why glass is transparent, we should ask why most objects are opaque. They are opaque because electrons absorb visible light photons. Electrons absorb the energy from photons to move to higher energy levels, making the object opaque. In glass, however, visible light photons don't have enough energy to excite the electrons. It can't excite the electrons, so light passes through, making glass transparent. But UV light has high energy. It can make the electrons in glass jump, so ultraviolet light can't pass through glass. Glass can block UV rays. This explanation seems logical. It suggests that photons not absorbed by electrons will pass straight through the atoms without any hindrance. However, that's not quite accurate. As light travels through glass, it slows down. For instance, if you shine a laser at glass, initially, the light moves at its usual speed in a vacuum. Upon striking the glass, it bends and decelerates to about 2/3 of that speed. When the light exits the glass, it resumes its original direction and speed. This phenomenon has been confirmed repeatedly without dispute, leading to the question: how does light pass through glass and why does it slow down? There are two popular explanations. One is that photons bounce between atoms as they pass through the glass. Even though photons move at light speed, their longer path through the glass means it takes more time to pass through. It seems like the speed of light has slowed. It seems plausible, but this explanation is wrong. Even if photons could bounce around within atoms, the direction and number of bounces would be unpredictable, as would the time and path they take to exit the glass. So, based on this explanation, when light strikes glass, photons scatter inside rather than exiting cleanly from the other side. The second idea is that photons are absorbed and re-emitted by atoms, a process that takes time. So, light slows down in glass because of this process. However, the issue is that when an atom absorbs a photon, it forgets the photon's original direction. The absorption and re-emission process happens randomly, meaning photons would scatter uniformly as they travel through glass. Thus, this explanation is incorrect. So, how does light actually pass through glass? Actually, all three explanations above assume light is a particle. But if you consider light as a wave, it becomes much easier to grasp light's everyday properties. Waves can overlap, and when their peaks align, they will combine to create a new wave with a taller peak. If the peaks and troughs of two waves are opposite, they will nullify each other. When the shapes and speeds of two waves in space are different, they will also combine to form a new wave. The wavelength, amplitude, and speed of the new wave come from the combination of the two waves. Glass atoms have nuclei and negatively charged electrons, while light is an electromagnetic wave. Electrons oscillate in light's electric field. The motion of these charged particles creates their own oscillating electric field, which merges with the light wave, creates a new wave that travels through the glass at a slower speed than light in a vacuum. This shows why light slows down in glass and speeds up when it exits, all while obeying the law of conservation of energy. So, someone might ask, if light is a wave, does a mirror reflect light by somehow bending the wave? Actually, that's not how it works. The metal coating on a mirror's back has many free electrons. When light strikes this surface, the electrons oscillate in the electric field, generating secondary waves everywhere. As per the Huygens-Fresnel principle, these secondary waves cancel each other out, except for those moving opposite to the incoming light, which combine to form a new wave front. This new wave is the reflected light from the mirror. Radar technology relies on this principle, meaning the reflected light is no longer the same wave as the incoming light. It's a new wave emitted by the mirror's electrons. Some materials absorb light, like most black substances, which neither transmit nor reflect light. This is because the electrons on their surface oscillate in the electric field of the light, making the whole atom move erratically. This converts light energy into heat. The electron movement also produces secondary waves. The object emits infrared light. Different materials have unique optical properties because of how their electrons are arranged. What do you think would happen if a beam of light passed through an object? According to the law of conservation of energy, your coin hasn't vanished, it simply moved from your pocket to mine. I'll take good care of it.